Hello. Okay, so hopefully today we'll get to finish off chapter 1, 2, which was the continuity of a function. So last time we talked a lot about sets and intervals, and the homework was the first couple of problems. So let's start with number 1. That was the first one that you were assigned to. So it gives us a function that looks, oh well, it's not too complicated, but it looks kind of messy. We have -2, and we have -1, comma 2. Comma 1. Then we have 3 over here. Okay, so 2. So we have 1, 2, 3, 4, 5, 6, and oh, we don't have 6, we just have 7. Okay, 2 comma, so it's defined here, it goes down here, and it goes up, and it goes down. Number 5. Then it goes up to 7, comma 3. And our function looks like this. Okay, so this is what our function looks like. It's defined from -2 to 7, so on that closed interval, and we're given 2 sets, and set A equals, remember, the bar method, the condition on the variable is on the right, all A, so that limit x goes to A minus f of x is not equal to limit x goes to A plus of f of x. And that's our set A, and set B is everything B that satisfies limit x goes to B of f of x is not equal to f of B. Okay, so what these two sets are saying is that they're basically different types of discontinuities, right? This one, the left and right limit does not exist. This one, the limit exists, but the function value does not exist. A thing to note about equations is that you may notice that for some of the x values, the limit does not exist, or for like -2 or 7, the left-hand or right-hand limit does not exist. For equations, if you're implying that something like P equals Q, for real numbers, this automatically implies that P exists and Q exists, right? So if either one of those does not exist, then the equation cannot be true, so it's false. So just keep that in mind when you're working these out. So number 1, this is the left-hand limit and this is the right-hand limit for set A. So we just have to look at everything that every point that does not have equal left-hand and right-hand limits. We don't have to consider -2 because the left-hand limit does not exist at all. So, okay, let's go to -1. The left-hand and right-hand limit does not exist. So that's a, how should we do this? Let's do A equals like that. And then we have -1. And we have, what else? 0, it's continuous. 1, we have different left and right hand limits. 2, we have the same limit, as well as 3, as well as 4. But 5, we have different left hand and right hand limits. And that's it for A. For set B, we have where the limit has to exist and the function value has to exist, and they cannot equal each other. So out of the points where the limit exists, we have 2, 3, 4, and 0 as well. But that cannot equal the function value. So 0 is automatically out for both 2, and 4, we have function values, right? But for 3, notice that there's no closed hole at x equals 3. That means the function itself is undefined, and this value is undefined. So we can't compare an undefined value, because they don't exist, right? So the only two elements in set B are 2 and 4. So that gives you, what are we trying to find? The number of elements in A plus the number of elements in B, and that equals 5. Okay, so that was number 1. The next one was number 3, I believe. Okay, so this was given to you as sort of like a challenge problem because it does contain composite functions. So let's take a look at the graphs of f of x and g of x. For f of x, we have this sort of function going on, -1, then this is 1, and then the function is defined here and here onwards, like that. Okay, so this is f, and g is -1, comma -1. So it's okay. Oh, must have been a typo. I think, you know what? We have two closed holes here, but I'm going to make this one open, okay? So that's a typo in the diagram that I showed you. Okay, so let's make this an open hole, and then the curve goes through like that to 1, 1. And then we have the function defined like that. Okay, so this is g of x. And select all statements that are true. So number A asks us the limit as x goes to 1 minus of f of g of x. So remember, when dealing with composite functions, the main idea is that we look at the inner function first, and then the output of that inner function becomes the input of the outer function. So let's take a look at g of x first. We go to 1 minus, we go that way. And remember, we have to watch what the output is. As x goes to 1 minus, y goes to 1 minus. So now we go to f of x and go to 1 minus over here. So that's here, and that's -1. So, no, the limit is not 1, right? It's -1. So A is false. B, function f of x, g of x is discontinuous at x equals 1. Okay, so we have f of x and g of x. So in order to determine continuity, we have to go from 1 plus and 1 minus, right? So at 1 plus, we have f times g. So let's take a look. 1 plus f goes to 0, and g goes to 0. At the function values, we have 0 times 1, and at 1 minus, we have -1 times 1 minus times 1, and that equals 0 and 0 and -1. So these do not all equal each other, right? So the limit doesn't exist, therefore the function is discontinuous at x equals 1. So that one is true. And number C, we're looking at the continuity of a composite function. So G compose F, remember the dot just means that G is the outer function and F is the inner function. So is this continuous at x equals -1? So we do the same process, right? We go to -1 plus, we go to -1 and -1 minus. But remember, we have to look at f of x first. So why don't we do f of x first, and then let's do g of f of x, like that. So -1 plus of f of x is going to be -1, right? As x goes to -1 plus. Right, so it does go to -1, but we're not approaching it, from like the bottom side or the top side. So what we can do is just straight in plug -1 into gx. So if we plug in -1 into gx, we get 0, right? So g of f of x will go to 0 when x goes to -1 plus. At -1, we have f of x equals -1. And then g of f of x goes to 0. At -1 minus, f goes to 0, not 0 plus, not 0 minus, and then we can go to 0 of g of x. Then g0 is 0, so we get that result. Therefore, all the limits, the limit is 0, and the function value, which is the middle one here, right? That's also equal to 0. Therefore, the function is continuous at x equals -1. So a couple of things to note about composite functions. If you want to scan for discontinuities in composite functions, what you have to watch out for is there's an outer function and an inner function, right? A discontinuity in the inner function would likely cause a discontinuity in the outer function, right? So that's number one thing to look for, is there any discontinuities in the inner function? Because the output can jump around. But even though the inner function might be continuous at that point, if the function value of that inner function causes a discontinuity in the outer function, then that can also be a problematic point, right? So what you need to do when considering composite functions is look at both the inner function and the outer function to see the potential points of discontinuity that they have to avoid like missing one. Okay, so the next question is number 4. So number 4 asks us, it gives us a piecewise function, which is very common in continuity questions. 3x plus 6 when x is less than 2, and x squared plus 8x minus 4 when x is greater or equal to than 2. And it says that this function is continuous on the set of all real numbers. Remember that polynomial functions are continuous on the set of all real numbers. So the only point we really need to consider is at the boundary of this piecewise, right? So the only point we need to consider is x equals 2, and it has to be continuous there. So therefore, the left-hand limit, the right-hand limit, and the function value must all exist, but the function value is covered by this side. So we only really need to compare this left-hand limit and the right-hand limit. So we can plug in x equals 2. So 6 plus 6 equals 4 plus 2a minus 4. So a equals 6. And there you go, there's your constant. So just remember, right, a continuity condition means that the limit must also exist. Okay, so for number 5, it's a pretty similar situation. F of x equals, but it's defined this way, x squared plus x minus 12 over x minus 3 whenever x is not equal to than 3, and we have a new definition of constant a at x equals 3. So for this one, the function value at x equals 3 is a, but the limit has to exist and must equal a. So when x is not equal to 3, that shouldn't be a problem, right? Because when we're taking a limit, remember, we're getting close to 3, but not actually equaling 3. So we can take the limit, x goes to 3 of this top expression, x squared plus x minus 12 divided by x minus 3, and we can factor it, right? This factors to x minus 3 and x plus 4, right? So x plus 4 is the only one that gets left. Limit x goes to 3, so that's 7. and that has to equal the function value, which is a. So you automatically get a equals 7. Okay, and number 6 and number 7 as well. Okay. Number 6, function f of x is continuous on the set of all real numbers. And we have two constants that we need to find this time, a and b. So for number 6, our piecewise function is f of x equals ax plus 1 whenever x is less than 1 or x is greater than 2. And then we have x squared minus x plus b, where it's in between, like that. Find a times b. Okay, so what we want to do is we want to consider where this function might have discontinuous points. And obviously, since these are polynomials, the boundaries that we need to look at are -1, 1 and 2. 1 and 2. So at x equals 1, the left and right hand limit must equal to each other. So let's plug in 1. A plus 1 equals 1 minus 1 plus b. So that gives us this relationship. And at x equals 2, 2a plus 1 equals 4 minus 2 plus b. And we can substitute, right? A plus 1 equals b. So 2a plus 1 equals 4 minus 2 is 2. And b is a plus 1. So a equals 1, 1 goes away. So a equals 2. And b equals a plus 1, which is 3. So a times b equals 6. Okay. So just again, for piecewise functions, all the interesting stuff happens at the boundary. Okay, number 7. Function f of x is continuous on the set of all real numbers and satisfies x plus 1, f of x equals x squared minus 2x minus 3. Find f of -1. Okay, so if you try to plug in -1, you'll notice that, to our disappointment, this x plus 1 term goes to 0, sending this entire thing to 0, and we never really know what f of 1 is. So we can't plug it in and exactly get what we want. But what we can do is we can rearrange this into f of x equals x squared minus 2x minus 3 over x plus 1. And suddenly you got a really familiar looking sort of rational expression. Remember that this function is continuous on the set of all real numbers, so the function value has to equal the limit value. So what we can do is, if we plug in -1, this will be undefined. But what we can do is we can take the limit x goes to -1. By dividing by x plus 1, we automatically assume that x plus 1 is not equal to 0. So this expression only holds when x is not equal to -1. Just note that, okay? So we can take the limit, because the limit really doesn't mean we're getting to the value itself of this, right? X plus 1, x squared minus 2x minus 3, and we can factor it. We can do 1 negative 3, so that's x minus 3. So limit x goes to 1 of x minus 3, and that will go to -2. So that is the function value that you're looking for, because the limit value has to equal the function value. Okay, so number 8. I think I'll leave that for homework. That's pretty similar to number 7. And number 9, for two functions, x squared plus ax, and that function g of x, find constant a so that f g of x, again, it's a composite function, right, is continuous at x equals 0. So for number 9, you know what? You guys can do number 9 since we talked about composite functions already. Try that on your own, and let's go to number 10. So number 10, we have a different scenario where f of x is a piecewise, where x plus 3 for x less or equal to than 1, and negative x plus 2 for any x that is greater than 1. And we have function g of x equals x plus a. And it says that f of x times g of x must be continuous at x equals 1. So at x equals 1, we need to consider 1 plus, 1, and 1 minus. So at x equals 1 plus, we have to go down here, right? So the function value of f of x is negative 1 plus 2, which is 1. And then g at 1 plus, well, g is just a straight line, so it's not going to matter anyway. 1 plus a. And f times g is 1 plus a. Now we compare the function values. Now you can notice that the function value is included up here. So the function value and 1 minus will be considered the same thing, right? So if we plug in x equals 1, that would be 4 for both. And then for g of x, it's going to be 1 plus a for both as well. So this will end up being 4 plus 4a. Now, this has to be continuous, so we have to set them equal to each other. Negative 3 equals 3a, so a equals negative 1. And find constant a, so that would be our answer, right? It's kind of like the same pattern, just with different functions and different scenarios. Number 11, g of x over f of x, right? I'll leave that up to you guys. And number 12 is f of x times f of x minus 1. I'll leave that up to you guys too. So I'll write down all the homework questions at the end. Number 13, function f of x is shown below. So we have a function that looks like negative 1 comma 2, 2, 3, and 2. Okay. So we have a line going here, and a straight line at 0, and then a line going up like that. So that's f of x. Select all possible functions y equals g of x so that the function f of x times g of x is continuous on the set of all real numbers. So the first candidate is a piecewise linear. So 1, 1, and 2, 0. So that's our first candidate for g. Our second candidate is this function at 1, 2, and 3. So that's, I think I labeled this G1 and G2, and our final option is G3. G3 is 1 and 2. Okay, so we have to figure out which one of these would work for negative 1 comma 3. Okay. So f of x, is there any discontinuities in f of x? We don't see any, right? It's a, for every point, we see a continuous function. Now, option A for G1, we also see that, that a function is continuous for all real numbers. So if you multiply a continuous function with another continuous function, will there be any discontinuities? The answer is no, right? Because for every point, the left-hand limit, the right-hand limit, and the function value remains exactly the same. So in the notes, I've shown you, you can add, subtract, multiply, or divide continuous functions and multiply constants to it. As long as the denominator isn't 0, the resulting function is always going to be continuous. Now, G2 tells a different story, right? This works, but this might not, because G2 is discontinuous at x equals 0. So let's focus at x equals 0. 0 plus 0 and 0 minus, we have f times g. Okay, at 0 plus, f is going to 0. At 0 minus, it's 0, and the function value is 0. G, the function value at 0 plus is 3. The limit to 0 plus is 3. The function value is at 2, and the limit to 0 minus is 1. So obviously, g of x is discontinuous at x equals 0. But what happens if we multiply all of these? They all go to 0 because f of x is sending them all to 0. So this actually works because the end result is all going to be 0. So this tells us that if a function is going to 0, then there could be a discontinuity in g of x, but the multiplied function will still be continuous because everything will go to 0. So this is one way to, get rid of a discontinuity, is to send something to 0 when two functions are multiplied. So the third option, C, let's see. X goes to 2. So the discontinuity is at 2. So let's consider 2 plus 2 and 2 minus. At 2 plus, f of x goes to, well, it goes to 0 again. So everything goes to 0. And although the limit and the function value equal each other, the limit to the left does not. And even if there is a discrepancy here, since f of x goes to 0, everything will go to 0 automatically, which means, turns out, all of these functions work. You can multiply a discontinuous function with a continuous function, and it will still get continuous at a certain point, right? Because we have to make sure that whatever discontinuity is here, we have to send it to 0. So there's two ways of resolving discontinuities. There might be a problem where it asks you to, determine a certain form of a function that will make the multiplied function f times g continuous. Number one is to send one of them to 0, right? We've seen that if f of x goes to 0, the other function g of x can be discontinuous, but the resulting multiplied function is still going to be continuous. Or number two is more like a special case scenario. You can have a discontinuous function multiplied by a discontinuous function. So at a single point, right? If a function is discontinuous at a single point, let's say like it goes like that and it goes like that. If this is 2 and 6, you can have the second function line up exactly at, I don't know, 3 and 4. Well, technically this is an open hole, but so that the left-hand limits, so we need to consider the left-hand limits. So the left-hand limits is what? 3 times 2. Then if I wanted to, then I can go put an open hole at 1 so that the function goes to 6 times 1, right? So 3 times 2 equals 6 times 1. So that would be a case where it makes it continuous. Discontinuous times discontinuous can be continuous as long as the numbers work out. So you have to make sure that whatever is multiplying works out with each other. So these are two ways to resolving discontinuities, right? Okay. Number 14. Let's see, is there anything more interesting? I'll leave number 14 up to you guys. And let's take a look at number 15. So number 15, the function that is written here, it's called the floor function. And the definition is described in the problem. For real number x, so it's written like this. This is called the floor of x. Let the floor of x denote the greatest integer that is not greater than x. So what does this mean? So if I have a number like 4 over 3, then the floor of 4 over 3 is going to be the maximum integer that does not exceed this number. So that would be, this is between 1 and 2, right? So the floor of 4 over 3 would be 1. It would be the less, it would be the one that is less than it. How about the floor of negative 2? Well, we need to select the greatest integer that is not greater than negative 2. So that would be itself, right? Negative 1 would be greater than negative 2, so that doesn't work. And the graph of floor of x, we can imagine it, and we need to draw it to get to this problem. The floor of 0 is 0, and the floor of everything up to 1 is still going to be 0. So we're going to start with a closed hole, and then the floor of everything is going to be 0 until we reach 1, right? Where the floor of 1 is going to be 1. So it jumps up like that, 1 comma 1, and then it continues, right? The floor of 1/2, 4 over 3, it's going to all be 1 until it hits 2. And then it jumps to 2, right? The floor of 2 is 2, so it jumps like that, and then it goes on like that. So it's kind of like a step ladder. They also call this the step function. So it's a series of flat lines defined like this. And what if we go to the negative side? Negative 1, the floor of negative 1 is negative 1. And everything after that is still negative 1, right? Because we're going for integers that are less than the number until it jumps to negative, at negative 2, it would jump to negative 2. And then it will stay like this until we get to negative 1. So it's the exact same pattern that's cascading down like that. So this is what we call the floor of x. And for how many x is the function floor of x minus 1? Discontinuous on the closed interval 0, 3. So I just drew floor of x, and I probably don't want to draw everything shifted to the right once more. So we're looking at the interval, closed interval 0, 3. If we shift this function 1 to the right, that interval would be from 0 to 3, but the original function is this shifted to the left. So we can shift our interval 1 to the left. So our new interval to analyze for this function is what? Negative 1 comma 2. So it's just a way of analyzing the base function instead of the shifting function. You can shift intervals to the left, right? Yeah. Okay, so from negative 1 to 2, so it's this interval right over here. So the only, let's see here. We're going to count discontinuities, and we can see the obvious ones, right? We can see this is a discontinuity, 1, 2, and we have to be careful when we get to the edges. This is a closed interval, so we have to consider, remember I told you there was an exception for evaluating discontinuities in closed intervals. The left-hand side, we do not need to look at the left-hand limit. We only need to look at the right-hand limit and the function value, right? So here, the right-hand limit is negative 1, and the function value is also negative 1. So that means that in this closed interval, this point is a continuous point. Although if we look at the entire function, it's definitely not. But on the right-hand side, the function value does not exist at all, which makes it a discontinuity, okay? So just that little distinction there. So there's a total of 3 discontinuous points for the floor of x minus 1. The floor function, you won't see that much in this course, but if a lot of like math competitions have you do quite some difficult problems with this floor function. So it's good to get yourself familiar with it. Okay. Ooh, number 16. Function f of x is continuous on the set of all real numbers, and on closed interval -1, 3, f of x is defined as follows. So on -1, 3, that closed interval, it's defined as ax plus 1 when x is between -1 and 1, and negative x squared minus 3ax plus b when x is like that. Okay. Additionally, it gives us that f of x plus 4 equals f of x. Now, after today, when you see these types of conditions, I want you to recognize what they mean. So let me introduce you to periodic functions. If you've done pre-calculus 12, then you should be very familiar with periodic functions because that's what trig functions are, right? But if you haven't, let's take a look. Periodic, it has a period. So period we usually denote it as p, and p is the smallest positive number that you can choose so that f of x equals f of x plus p. Okay, so what does this mean? Let's say I have a function that is defined like this from 0 to 2, okay? And what I want to do is I want to repeat the pattern. Let's just do it like that. I want to repeat the pattern. So I go the exact same shape like that, and then we end up at 4, right? And then I repeat this pattern again, identical shape, and then we end up at 6. So the period is basically the length in which this pattern repeats, and we want the smallest positive length. So the period of this function, obviously, if it's defined on the set of all real numbers, we'll have another, this will extend into the negative numbers as well. So the period of this function is 2 in this case. So whenever you see conditions like this, f of x plus 4 equals f of x, oh, you should immediately realize that what? F of x is a periodic function with period 4, meaning for every 4 length in the x direction, the pattern will be exactly the same and will continue on forever unless we have like other restrictions. A thing that some exams or teachers will do is they will slightly modify this condition to make it look less obvious. What they will do is they'll plug in x minus 2 into this equation, and then this will be x plus 2 and x minus 2, right? So f of x plus 2 equals f of x minus 2. So they'll slightly switch up the situation here. So f of x plus 2 equals f of x minus 2. You should be able to comfortably revert this back and realize that this is a condition on the period of the function. Okay, so let's go back here. On the set of all real numbers, -1 to 3. And what do you notice? The period is 4, right? The period is 4. And this interval length happens to be 4, right? That's not a coincidence. It's the problem giving you just the right amount of information, because this interval will then what? Repeat itself over and over again, and it has a length of exactly 4, and the period is 4. So always notice those little things that are given to you in the problems. Every number may have a significant meaning to it, especially in harder problems. Okay. It's continuous. It's continuous on the set of all real numbers. Okay. So from -1 to 3, we don't know what the function might look like. It might look like that. I don't know. Well, it's a piecewise, so it might look different. But it's continuous on the set of all real numbers. So that means what? This is going to repeat itself like that. And you notice this discontinuity that happens at x equals 3, right? This end value and this end value, if they don't equal each other, then the function is obviously not going to be continuous. But this value, remember, since it's periodic, will always equal this value, right? So for all we know is the function between -1 and 3. And if the function has to be continuous for the set of all real numbers, then this function value and this function value have to equal each other, so that when it's equal to each other, if it goes like that and that, then we'll keep having like this pattern, right? So that for every boundary, for every 4 periods, we have a continuous function. And notice that function f of x itself, right here, there's also a boundary, right? So we have to consider that as well. So we have 2 equations and 2 variables, so we can deal with that. Okay, so number 1 is the internal, right? Internal continuity check. The boundary is at 1, right? It changes at 1. So a plus 1 equals -1 minus 3a plus b. So if we rearrange that, b equals 4a plus 2. Number 2 is the endpoints. The endpoints have to equal each other because this periodic function has to be continuous on the set of all real numbers. So the endpoint is at -1, and this one, the endpoint, is at 3, right? So we plug in -1 minus a plus 1 equals -9 minus 9a plus b. And now we know that b equals 4a plus 2. So 8a minus 8, no, 8a plus 10 equals b, right? And that is 4a plus 2. So 4a equals -8, so a equals -2. A equals -2, and b equals 4a plus 2, which is -2 plus -8 plus 2, which is -6. So therefore, we can find f of 10. What is f of 10? So you notice that f of 10 is outside our -1, 3 range, but remember, it's periodic, so we can go backwards 4 spaces or forwards 4 spaces. And in this case, we want to go backwards, right? So f of 10, I'll just erase this diagram here. F of 10, we go back, and then we go to f of 6, right? And we're still not in this range, and we go another 4 spaces back, and that's equal to f of 2. So now we know that f of 2 has to be on this function, so we can plug that in, -4, and a is -2, so 6 times 2 plus b. b is -6. So it's 12 minus 10. Oh, 12 minus 10, which is 2. So our final answer for this would be 2. So this problem, right? We define what the periodic function is and the continuity conditions for a periodic function. Okay, so that was pretty important. Number 17. So number 17, we have 2 graphs. For real number t, let f of t denote the number of intersections between the graph y equals t and y equals absolute value of x squared minus 1. Now, this is a very common pattern for difficult problems. They give you f of t. Have we seen a function defined by the intersection of the 2 graphs in this specific context before? No, right? So it gives us an unfamiliar function to deal with, and we have to answer all kinds of problems about f of t. So how do we analyze an unfamiliar function defined this way? Well, the best way to do that is to start drawing or modeling the situation and start plugging in some values and start collecting some examples and start moving around t so you can get a feel for what this function is all about, right? So we have the graph of y equals absolute value of x squared minus 1. So it's like that, right? In case you forgot how to draw absolute value graphs, if there's anything below the x-axis, right, you just flip it up, right? Because it's the absolute value. You flip up anything that's below the x-axis, and there you go. This is the absolute value graph that you have. So for y equals x squared minus 1, this is what the absolute value would look like. It has roots at -1 and 1, and the bottom portion is flipped up like that. Y equals t. That's just a horizontal line. Remember, t is the variable of f of x, but right now we're drawing the graphs of y equals t. So in that moment, t acts as a constant, and we can just draw a straight line. T might change, right? The straight line might be down here or up there, and t moves around. But in each one of those specific scenarios, t is just a straight line, right? So another thing to keep track of when solving difficult problems is, in this context, like, what is a variable and what becomes a constant? Although t can be varied, when we're drawing the graph, t is a constant function, right? And a lot of people really get confused about that, especially in difficult, calculus problems in the full course. So select all that are true. So if the horizontal line, y equals t, is down here, do we have any intersections between the graph of this absolute value and this horizontal line? We don't, right? We can slide it down further and further, but we're not going to get any intersections until we slide it up and t equals 0. Then we'll get two intersections right away, right? So if we can draw f of t, this is how we can visualize it. When t is negative, there's nothing, there's no intersections. So the function will keep going at 0 until we hit t equals 0, and then it will immediately jump to 2. And then we can keep going up until, oh yeah, and if we go up just a little bit more than 0, then how many intersections will we get? If we go to, like, imagine you go to 0 plus, you go slightly above, immediately we get 4, right? We get 4 intersections. So this is what will look like. We can slide it up and keep getting 4 intersections until we hit t equals 1, in which case this will be a tangent point. So we only get 3 intersections. So it will it will remain at 4 until t goes to 1, and then it will spring down to 3. Sorry, not 2, to 3. And then just after that, it will have 2 intersections. So we'll go back down to 2. And then once we go past this point, we can keep sliding it up. There will always be 2 intersections. So this is what our graph of f of t looks like, and now we can analyze it. Number A says f of 1 equals 3. Oh, this should be a closed hole, right? Because it's not defined, it's just defined after that. So f of 1 equals 3, yes, because the function value here is 3. Number 2, limit t goes to 1 minus of f of t equals 4. So 1 minus would be that way, and that value is 4, so B is also correct. Number C, f of t is discontinuous at 2 points on the open interval -1 to 4. So basically -1 is over here and 4 is way over here. How many discontinuous points? We have 1 here and 1 here, and that's it, right? So C is also correct. Right, so we got our first taste at analyzing a newly defined unfamiliar function. And you'll see a lot of these as we progress through our course. All right, number 18. Remember that this is the union symbol, right? The cup symbol, and I encourage that to for you to do as homework. Number 19. Number 19. Find the sum of all integers a so that the function f of x equals x plus 1 over x squared plus ax plus 2a. Okay. We have f of x equals x plus 1 over x squared plus ax plus 2a. And this has to be continuous on the set of all real numbers, and a is an integer. Okay, how can that be continuous on the set of all real numbers? Well, we have to ask ourselves, if a function has to be continuous on the set of all real numbers, are there any potential points of discontinuity? I think I said last time that for continuity, you want to focus more on the discontinuous points than the continuous points. Now, what in any way can this function be discontinuous? If you look at it, it's a rational function, which means that always the denominator is the more troublesome one, right? If the denominator equals 0, then we might have a constant over 0, which would be infinity, and the function won't be defined there. So the first case that we can consider, right, is denominator has to not equal 0, right? Then we're sure that this the limit will exist, and it's a ratio of two polynomial functions, which is continuous divided by continuous, where this is not 0, so the whole thing will be continuous. So we just have to make sure the denominator does not equal 0. But a case that a lot of people miss, they just do this and move on. But we have to be careful. We have to consider every single case. Number 2, the denominator equals 0. And remember, when we were evaluating limits, we did the factoring out all the time. What if this has a factor of x plus 1 and that goes away and we have a perfectly good limit value, right? Oh, but this is continuity. Oh, never mind then. Then if the denominator is equal to 0, then the function value itself won't exist. So we don't need to consider this. But if the question said the limit exists for every real number x, then we would have to consider that case too. But we're talking about continuity, which is stricter. The function value also has to be defined. So this is all we need. Okay, so x squared plus ax plus 2a cannot have any roots, right? Because that's what this translates to. Any roots. Remember that this is a concave up parabola, so it has to be like this. It can't touch it or it can't intersect it at 2 points. Then we'll have points where the denominator is 0. So it has to be above the axis and not touching the x-axis, which means that the denominator, the discriminant has to be less than 0. So let's take a look at the discriminant. A squared minus 4 times a times 2. So that's 8a has to be less than 0. And if we solve that, that's what, 0 and 8. So a has to be between 0 and 8, and a has to be an integer as well, right? So the sum of all integers is the sum from 1 to 7, which is what? 7 times 8 divided by 2, which is 28 would be your answer here, okay? So this is actually an easier version of the problem, right? If it said that the limit exists for all real x, then you would have to consider the case where the denominator is 0, but this might factor out. But since this is continuity, this is all you will have to consider for this problem. Okay, so that was number 19. Number 20, I encourage you to do on your own, right? It's similar to number 26 from chapter 1.1. You can test your logic, and if you want to prove something that is false, it's way easier because you can find one single counterexample. So what you might do is you might want to search for those counterexamples first, and then if you can't really find a counterexample, you have to make a formal reason why this must be true for all cases. Okay, before we continue to the other problems remaining, let's do some work on the final pieces of information in this chapter, which is the extreme value theorem and the intermediate value theorem. Okay, so if you look at your notes package on page 6, so the extreme value theorem sounds cool, but it's not much. It will seem quite obvious to you. So what the extreme value theorem is telling you is that if function f of x is continuous on the closed interval a comma b, then it has a maximum and minimum value on this interval. Now this seems pretty obvious, right? What are some cases where a function might not have a maximum or minimum? If a function is defined like this, and we want to analyze like this interval, then we can say that, hey, this is an open hole and it's not defined anywhere else. We can keep getting closer to it, right? But does a concrete minimum value exist? A minimum value means it has to be a real number. Here, there's nothing defined, and we can get to, like, if this is 1, then we can get to 1.1 and 1.001 and 0.0001, but will we actually get to a concrete single real number? No. So this case, the minimum value does not exist, but the maximum value will exist, right? It's just this value over here. What the extreme value theorem tells you is that continuity on a closed interval guarantees that you will have a maximum and minimum value of that function on that closed interval. Because if this function has to be continuous, then this has to be filled in because the limit has to equal the function value. So whether the function looks like this or like this, if it's continuous on the closed interval that you choose, it will definitely have a minimum or maximum value. And if it just says minimum or maximum value, some people call it absolute minimum and absolute maximum. We'll talk more about that when we get into analyzing more functions in the next unit. But notice that if I have a parabola, right? When we were talking about minimum and maximum values on a parabola, and we have a left end and a right end, the maximum value does not necessarily happen on the ends of the interval. It could happen right here, right? Between the intervals. So just make sure that you're checking all possible points where it might be a maximum. Okay, so that's what the extreme value theorem is. The more important one is the intermediate value theorem. And this theorem, we call it IVT for short a lot because it's just what it sounds like. It's an intermediate value. Okay, so the condition for this is the same. If f of x is continuous on the closed interval, AB, and okay, and let's say there has to be one more condition. F of A has to not equal f of B. So what's happening here is that we have maybe a point that is lower or higher than the initial point. and we have to have a continuous curve or a graph that goes through these 2 points. So maybe like that. Like that. Or it might be anything, but it has to be continuous. Then we can say that for any constant k, so we're going to choose a constant k, but k has to be between f of a and f of b. For any constant k between f of a and f of b, there exists constant c so that f of c equals k. Okay, so what does this all mean? So remember, the y-coordinate of this is f of a, and the y-coordinate is f of b, and the x-coordinate is a and b, right? I'm going to choose any constant between these two numbers, between f of a and f of b. Let's say I pick this one, okay? This is the k that I pick. The intermediate value theorem, so k is kind of like the intermediate value here. It guarantees you that there must be a constant c so that the function value of c is equal to k, i.e. the function actually intersects with this intermediate line at least once, right? If I choose k to be like that, I could get more than one possible values for c, but if you're connecting 2 points with a continuous curve and you put a horizontal line, so that value anywhere in between, it's guaranteed to cross that line exactly once. This one, I think it's also kind of intuitive, right? You have an infinite line that you have, and then you have to get from one side of the line to the other. And remember, this is like the intermediate value is k, so it's like a horizontal line stretching from negative infinity to infinity. A continuous curve has to happen, so you can't, just randomly lift the pen somewhere and go somewhere else. You have to draw a continuous curve, and then you have to cross it at least once. You can cross it multiple times if you want, but the point is there is at least one guaranteed value where you'll cross the intermediate line. So that's what's called the IVT. And there's a couple applications of the IVT, which we'll get to in our problems. Number one is we can find a root of a function. So remember the analogy of crossing a line at least once if you want to get to opposite sides of that line. So if I have the x-axis like that, and I know that something is negative, and I know that something is positive over here, then I can guarantee that as long as the function is continuous, I will have at least one root in this interval, okay? So we'll get to that in our workbook. So back to our workbook. Number 21, I will leave that up to you, right? That's the extreme value theorem. You just want to check if a concrete real number, a single concrete real number exists as the maximum or minimum value in that interval. So number 21 is for homework. Number 22, for what range of constant a does the equation x cubed minus x squared plus a equals 0 have at least one real solution on the closed interval 1, 2? Negative 1, 2, sorry. Okay, so we haven't learned how to solve cubic equations yet, right? And we won't be able to do much anyway because we want to find the range of a. So number 22, we can recognize that this is an intermediate value theorem because it gives us an interval for us to work with. The real solution just has to be between negative 1 and 2, right? So remember, we can visualize this if we want to. Visual reasoning is always pretty nice. There has to be a root in between here. So that means whatever function value, it has to be below. Can it be at x equals 0? Think about that. It can be at x equals 0 because we're talking about an open interval. So this point can slide all the way up to 0 if we wanted to. But if it's below the line, then the function value at x equals 2 has to be above the line, which is the x-axis, so that once we have a continuous curve, it will cross it at least once. Now this can be swapped, right? This might be above 0 and this might be below 0, but the ultimate point, whatever the case, it might be like this and like that, and be like that. Whatever the case, the sign of the two function values have to be different, right? Or it can equal 0 in this case because we're talking about a closed interval. So let's take a look at f of, let's call this a function f of x, okay? F of -1 equals -1 plus, no, -1 minus 1 plus a, which equals a minus 2. F of 2 equals 8 minus 4 plus a, which equals 4 plus a. So if we multiply this, a minus 2, 4 plus a, then it has to be less than 0, or it can be equal to 0 because we're looking at a closed interval, and if it's equal to 0, then that would be the root of the function, right? So now we can solve it, -4a2, like that, right? How, so for what range? For what range? Then we can highlight this as our answer, okay? Okay, so number 23. I'm not going to solve this for you, but there's a word that you might have not recognized here before. Simple root. So I'm going to explain to you simple roots versus multiple root. So a simple root is in factored form, right? When you're factoring a polynomial to solve it, only one of them is multiplied. So the power is 1. And a multiple root is you have a root that is multiplied twice or 3 times or 4 times. So x minus alpha squared or x minus alpha cubed or higher in its factored form. A simple root will look like this, right? We'll talk more about this as we go to polynomial functions, but you can think of this as a line, right? A line going through alpha. A multiple root, we're familiar with this, right? Y equals like x minus 3 squared. It's going to be tangent, but it will go back up at x equals 3, right? So it will either be like this or like this. And x to the x minus alpha to the power of 3. If you've looked at the basic function y equals x cubed before, it will sort of look like that, but you don't have to worry about this too much. Okay, so this is true where this picture, this going from negative, being tangent and going to positive infinity, is true regardless of the number. It can be any odd number that is greater than 1. And at x equals alpha, if you zoom in, it will look like this. For this, also, this can be any even number. And if you zoom into x equals alpha, you'll see a picture like this. It will be tangent like this, and then it will go back up. I'll explain why the picture is like this fully when we get to differentiation. But right now, think of it as a line and a parabola going like this. It depends on whether this is even or odd, okay? So that should inform you for number 23. And number 24 is quite an easy application problem. So I'll leave that up to you as well. Okay, so for homework today, I'll write it over here. You'll see that many of these problems have, a repetitive structure, but I think each problem has its own unique situation. So number 8, and I think I assigned you number 9 as well. Number 11 and 12. Number 14. We did numbers 15 and 16. We did 17, 18, 20, 21, 23, and 24. Okay, so that's how many? That's just 10 problems for you to work on. So with after we solve these problems, then we will be done with Unit 1. So next class, I won't be here on Thursday, but next Monday, we'll go over the homework problems and we'll go over what's going to be on the Unit 1 exam. So there's 3 units. There's going to be a Unit 1 exam, a Unit 2 exam, and a final exam after Unit 3 that covers everything that we've done. So Unit 1 is on limits and continuity, and we'll cover more on what's going to be on the exam, what's its format, what am I going to be able to solve next class. So take a lot of time to solve these questions and start reviewing Unit 1 as well if you need it. And I will see you next class. Okay, goodbye.